In a practical push-pull converter, there is one issue called the flux walking. We will try to discuss and try to understand what flux walking means and how to take care of this. Let me first draw the push-pull circuit. I am going to focus myself only on the primary side. So you have the two transistors, the battery here. On the common core you have the secondary and the secondary center tapped, and you have the further portions of the circuits here, that is the two diodes, the inductor, capacitor, the buck converter, complete buck converter. But I'm not going to draw this here, we know that, because I want to restrict myself to this portion of the circuit here on the primary side and see what is this flux walking. It is a serious problem in practical circuits and which can cause damage to the topology itself. It could blow up the transistors and it could cause saturation of the transformer. So let us see how this happens and how we can solve this problem. So let me mark these dot polarities here for the transformer. This is Q1, this is Q2. Let me mark VI here, and let me also put in this waveform that we need to understand. And here I am going to draw only one waveform, and that is the primary voltage here, V primary. I am picking the entire primary coil. One could pick any one of the coils, either the primary or secondary, it doesn't matter, because the flux inside is the common one linking all the coils. But it is easier to draw the waveform for the primary, so therefore I will draw that. All the waveforms are similar, but easier to understand just with the complete primary. So let me draw the time axis, and let me mark the label here V primary, the voltage across this entire primary. Now we know that during the time periods when Q1 and Q2 are off, the voltage across the coils are 0, because the output side inductor, the buck converter inductor, is freewheeling and it is splitting across the secondary center tap secondary coils and causing opposing MMFs to come up, and therefore d phi by dt is 0. No voltage during the time when Q1 and Q2 are both off together. Therefore during all those periods you will see 0 voltage across the coils. So that's what I am marking here. And during the time when Q1 is on, you will see that the non-dot end will be connected to the ground, 0 potential. The dot end is connected to VI, and therefore the voltage here would be VI with dot end positive. So all the dot ends will be positive with respect to its non-dot end. Here also dot end will be positive with respect to the non-dot end, even on the secondary side. So this we know. The voltage will be VI and VI. This is what will be induced across the primary coils. So therefore if I take the entire primary coil, it is VI plus VI, which is 2 VI. So let us mark that here. During the time when Q1 is on, the primary voltage with the dot ends being positive, you will see a voltage of 2 times VI. And during the time when Q2 is on, the dot end is actually grounded. The non-dot end is plus VI, and this minus VI is induced on all the coils. So therefore let me place the polarities in this fashion. Non-dot end is positive with respect to the dot end. Same with all the other coils too. And on the primary side you are seeing VI with the non-dot end positive, so it is a minus voltage that you will see across the primary, and that will be minus 2 times Vi. So this will repeat cycle by cycle. Second cycle it is 2 Vi positive minus 2 Vi negative when Q2 is on, so on. So if we connect them all together, you see a waveform like this, and this is the type of the waveform that you would see on an oscilloscope when you probe the entire primary. You will see that it is also, you will get similar waveforms across each of the secondaries, but they will be scaled by the turns ratios. Now let us see the problem. What is the problem? Now in a practical circuit, when all the devices are considered ideal, we are expecting that the voltage, positive voltage, the area here, volt second, and the negative voltage second here, these two should exactly balance so that there is no average. So this is the physical nature, the fundamental physical nature of the coil, where you cannot have an average voltage across the coil. Okay, now in the case of a practical situation, if you look at this voltage here, this is the time during which Q1 is on. Now Q1, when Q1 is on, in an ideal case, we say that the ground is connected to this point, which means that VCE sat is equal to 0. But in a practical case, the VCE sat is not 0, so therefore it will be Vi minus VCE sat 1, which will appear across this, and that's what will be induced with proper scaling. So Vi minus VCE sat 1 is appearing across is appearing across the primary coil connected to Q1, and 2 times that will be appearing across the entire primary coil. Likewise, during the time when Q2 is on, you will see 2 times Vi minus VCE sat 2 coming across the primary coil. So if you look at this, there is volt second balance, perfect volt second balance, only when VCE sat 1 and VCE sat 2 are equal, same. But in a practical situation, it will not be. You should also understand that the time period is DTS when Q1 is on. You would also be giving control signal DTS for Q2 to be on during the same time period. So if VCE sat 1 and VCE sat 2 are mismatched, you can have a difference in the area. So if VCE sat 1 is not equal to VCE sat 2, then there can be a small average here. It can be a very small average. We'll call that one as V primary average. It could be as much as a microvolt, but doesn't matter. So even if it is a microvolt, you will have a problem. That is because from the Faraday's equation, V primary average, which is equal to NP, if I consider the number of turns NP for the whole primary, d phi by dt. This is Faraday's law. So what is flux? Flux is V primary average, which is a constant dc divided by NP integral dt, which means that phi is proportional to t. This is constant, integral of dt is t. Phi becomes proportional to t, which means that the flux is increasing continuously with time. Whatever may be the scaling, V primary average may be 1 microseconds, which means that the phi will continuously increase and probably reach saturation after a few months. But still, you will have a problem, which means that initially the circuit will be working, and after a few months, after the flux saturates, you will see misbehavior. It may be catastrophically damaged by blowing up some of the components. So what happens is that the operating point keeps drifting depending upon whether V primary average is positive or negative. It will drift to plus phi m or minus phi m and ultimately saturate the core in one direction. So once the core saturates, when you give a duty cycle T on, there will not be induction and the current will increase and blow up the switches. So this is the problem in a practical case. You cannot make the transistors perfectly matched. It is not possible. So you will land up with VCE-SAT1 not equal to VCE-SAT2, and you will have this problem of flux walking. So how to solve this problem electronically? So that's what we will be looking at next. Let us now try to visualize the effect of flux walking on the primary voltage waveform. So let me draw this BH curve here, a typical BH curve of the core using the push-pull transformer. And normally the operating point, the average flux value operating point will be in the center here. Average flux will be 0. And about that average flux, you will have the swing going plus and minus phi m. Now, if you look at the average flux in a practical push-pull converter, we saw just now that the average flux was proportional to time t, which means that it starts growing. It grows from 0 in this fashion. And at somewhere here, you will see that the average flux point will be somewhere at this point, away from 0. I have shown it positive. Of course, it could also be negative. You could have the flux decreasing. So you will see that the swing will still be about that average flux operating point, and you see that it is near at the top end, at the positive side. You will see that it is near the knee of the BH curve. Still, there is no damage done as yet. Now, as time progresses, somewhere here, let us say at this point in time, you have still a much higher average flux somewhere here. And when you take the swing about the average flux operating point, you see that a portion of the curve on the positive side is moving on the knee, which means d phi by dt there is lower, and because the d phi by dt there is lower, you will see that the induced voltage or the back EMF across the primary winding will be lower, and as a result there will be a drop in the voltage. So let us have a look at that voltage across the primary. So the voltage across the primary is like this. We just now saw this V primary. And as it is swinging in the linear region, there is no change in the d phi by dt rate here, or even in this case, there is no change in the d phi by dt rate. So the primary voltage waveform will look essentially like this. Now, in this last case, where a portion of the flux operating region is moving towards the knee, the d phi by dt there is decreasing, and you will see a drop in the induced voltage across the primary. So this drop in the induced voltage of the primary can cause a high inrush current, because Vi is fixed, constant, applied as the input. The primary is showing a lower back EMF, and the difference in the voltage Vi minus this lower back EMF will cause a large inrush current, and which can blow up the devices. And it is against this problem that we have to protect. So as the flux walking continues, you will see that there is a drop in the induced EMF across the primary due to loss of induction, and as a result a high inrush current and damage to the transistors. So this is the problem of the flux walking, and let us see how we can avoid that. Let us now see if we can have a solution for the flux walking problem. So let me again draw the push-pull circuit topology, and I am focusing mainly on the primary side, because we have to control the pulse widths of Q1 and Q2. So let me draw that portion of the circuit and bringing your attention to Q1, Q2 switches. And we have a common core on which we have the center tap secondary. Let me draw the dot polarities like this. Now here you have the diodes, O-ring, inductance, capacitance, load. Okay, so the buck portion is there, and we know how that works. Now I'm going to put on the same core two more windings. One winding, these are all very low power windings, very thin wire gauge. They are used only for sensing. So dot polarity like this, note that I am going to put another winding there, dot polarity in the other direction. So this is going to sense. This dot polarity will be positive when Q1 is on. When Q1 is on, the dot is positive, so this will be positive. And when Q2 is on, the dot is negative, the non-dot end is positive, so the non-dot end. So I am basically trying to use sense coils and sensing the dot side and the non-dot side positive under different switch on conditions. So let me go further in the circuit. I will put a diode, so which means that I just need to have the positive. It's a clipping circuit. It clips and takes only the positive part of the pulse across the primary and finds an average. So basically I am trying to find the volt second. So this will find the average. This is an averaging circuit, RC. I am putting a simple averager. I could also use an op-amp averager to get better precision. And then for the other winding also I am clipping and then putting the RC averaging circuit. This is just to indicate conceptually that I am trying to take the positive part of this pulse, V primary pulse, and then averaging it to get the volt second, and the non-dot end during the time when Q2 is on, that part I am taking it out and finding the average, so that I have the volt second of the positive part of the voltage, V primary voltage, and the negative part of the V primary voltage. So this I will call volt second of Q1, volt second of Q2 during the time Q2 on, volt second when Q1 is on, volt second when Q2 is on. So these two should in actuality be same under normal operating conditions. But if they are not same, we have to do corrective action. So let us say I subtract them, plus and minus, and take the error. So the error, if both are same, should be 0. But if one is saturating and the other is not saturating, then this error will be finite. The error can swing positive or negative. So you pass it through a PI controller. So the job of the PI controller is to make the error 0 by giving a corrective voltage, V correction. This correction voltage should be added to the duty cycle patterns of Q1 and Q2 in such a manner that error here becomes 0. Error here becomes 0 means Vs volt second of Q1, then Q1 on, and volt second and Q2 on will both match. So this will take care of the differential VC sats of the devices. Now where do you go and give the correction? So normally under normal condition you will have a control scheme like this, where you have a V0 reference and you have a V0 feedback coming from the output of the converter. Then the error is given to a PI controller. The output of the PI controller is compared with a triangular carrier, plus minus in this fashion. So after the comparison of the control voltage, the triangular carrier, you will get a PWM voltage here, and this PWM is steered alternatively to go and switch Q on and then Q2, Q1 and Q2, Q1 and Q2. So the steering logic will act in such a way that Q1 and Q2 are mutually exclusive when they are turning on. So you will have the drive for Q1 and the drive for Q2, and goes to the base drives or the gate drives of Q1 and Q2. So this is how the normal PWM switching pattern will work. I will discuss this in greater detail shortly, but for now we will consider it as a block scheme like this. Now we need to add somewhere here this correction, because Q1 is getting a drive pulse DTS for a DTS period of time, Q1 is on. For mutually exclusive DTS period of time, Q2 is on. So let us say here I introduce something there, and then take this correction, and then the correction is passed through some logic, let us say, and then it is connected to these points, basically to let us say it subtracts from one and adds with the other the pulse widths. So which means that here in this case, let us say if the volt second when Q1 is on, that part is increasing, that part is saturating. Now you need to decrease that volt second, so you are subtracting some amount of pulse width from here, and then adding some amount of pulse width to the Q2 drive, so that Q1 is turned on for slightly lesser time than Q2, and then there will be a balance achieved. E will go to 0. Now this is the nature of the correction logic that we would use for correcting the flux walking. So as the flux tends to walk positive, let us say, then whenever Q1 is on, there will be a tendency for the back EMF induced when Q1 is on to reduce slightly when it reaches the knee, and that will be detected. So you will see that that value will be lesser than this value, and then the correction value will go positive in a way such that you can add and subtract here, such that Q1 and Q2 will automatically correct each other. So they will not be given same DTS. In the earlier case, open loop case, the DTS of both would have been same, but DTS will get corrected by the PI controller in such a fashion that Q1 will be again brought back below the knee, and the average flux will tend towards the 0 point. So this is the effect of the closed loop, which will be happening continuously and then prevent the flux walking. Of course, I have shown all this in a kind of a block schematic way. I will in detail show what is actually the logic, so that you will understand that.